astronomers have just confirmed something extraordinary. A brand new interstellar visitor named 3IATLAS, only the third of its kind ever seen. NASA is calling it a comet, but astrophysicist Suzanne Falsner thinks it could be something far more important, a planet seed, the kind of object that might help young stars grow giant planets much faster than dust and gas could manage on their own. So, let's break this down into three big questions together. First, what makes 3IATLAS different from ordinary comets? Second, how could Falsner's planet seed theory finally explain why giant planets form so quickly? And third, what does this mean for the way solar systems like ours are born? The first clue came from its unusual path. Unlike local comets, which loop around the sun in predictable ellipses, this one follows a hyperbolic trajectory, proof that it came from outside our solar system and will never return. That puts it in rare company. So far, only two other interstellar objects have been confirmed, Oumuamua in 2017 and 2I Borisov in 2019. Each surprised astronomers in different ways. Oumuamua sped up in ways that couldn't be explained by normal comet physics, while Borisov looked more like a textbook comet but carried unusual chemical fingerprints. Now, 3IATLAS joins the list. Clearly comet-like in some ways, but still packed with mysteries that prevent scientists from putting it neatly in one box. For now, most researchers lean toward calling it a comet, since sunlight heating its icy surface can produce jets that act like tiny rocket thrusters, nudging it off course. But those odd details, the unexpected chemistry, the strange activity, leave the door open to more adventurous ideas. Some of you might remember Harvard's Avi Loeb, who stirred debates by suggesting objects like these could even be alien technology. No proof yet, but it shows just how unusual these visitors can be. Yet for many astronomers, the real excitement lies not in alien speculation, but in a deeper scientific question. Could interstellar objects like 3IATLAS be key players in planet formation across the galaxy? This connects directly to a puzzle that's been frustrating scientists for decades. How do giant planets form so quickly? Here's the problem. Our standard models say planets grow slowly. Tiny dust grains collide, stick, and gradually build larger bodies. But when particles reach the size of pebbles or boulders, they tend to bounce off each other or break apart, hitting a growth barrier. That makes it almost impossible to build giant planets within the short window of time available, since a young star's protoplanetary disk, the nursery of planets, usually disperses in under 10 million years. And yet, telescopes keep showing us giant planets around stars that are only a few million years old. Clearly, nature is cheating somewhere. This is where 3IATLAS enters the picture. At a planetary science conference in Germany, Suzanne Falsner proposed a bold solution. Maybe young stars don't always start from scratch. Instead, they might capture interstellar visitors like comets or asteroids, objects already formed around other stars and later ejected into space. If such a body drifts into a young star's disk, it instantly becomes a ready-made planetary seed. A big head start compared to starting with just dust. From there, gas and dust can pile on rapidly, turning a small captured object into the core of a giant planet much faster than we thought possible. Imagine the scene inside a young star's disk. Tiny grains of dust swirl around, colliding endlessly, but most of those collisions don't stick. It's like trying to build a skyscraper out of soap bubbles. The pieces just break apart. But if something already big is there, like a wandering interstellar rock that stumbled into the disk, the whole story changes. Suddenly, instead of dust endlessly failing to merge, you've got a solid foundation. Every new particle has something worth clinging to. Growth goes from fragile to unstoppable. For gas giants, this is a game changer. These worlds need hefty cores, and they need them fast, before the star's gas disk evaporates into space. Falsner's models suggest that larger stars have a special advantage. Their powerful gravity acts like a galactic magnet, pulling in more of these wandering seeds. Even though their disks don't last as long, the jump start from captured travelers gives them the head start they need. And sure enough, when astronomers look around the galaxy, they find giant planets clustering around massive stars more often than around small, faint ones. Suddenly, the pattern makes sense. Now, this doesn't mean the old ideas are wrong. Theories like pebble accretion, where centimeter-sized particles spiral inward and pile up, or gravitational instability, where whole regions of gas collapse under their own weight, are still in play. But Falsner's idea of planet seeds adds another layer. Think of it less like a replacement, more like another tool in nature's kit. Planets may not form in just one way. Instead, it might take a mix of strategies, a captured seed laying the foundation, with local processes building the rest. Seen through that lens, 3IATLAS isn't just some weird comet passing through, it's living proof that these cosmic seeds exist, and a clue to how they might help star systems grow their worlds. If Atlas had wandered into the right neighborhood at the right time, it could have been swallowed into a protoplanetary disk and transformed from a lonely traveler into the heart of a new planet. That thought alone shifts how we look at interstellar visitors, no longer as rare, quirky passers-by, but as active players in shaping the galaxy's planetary diversity. And if Falsner is right, the implications are massive. First, it solves a nagging problem: how gas giants form so quickly. Second, it suggests that planetary systems aren't isolated islands. They're part of a bigger galactic exchange. Over billions of years, stars may have been quietly swapping building blocks, passing seeds from one nursery to another. Which means our own Jupiter might carry a piece of history that didn't even start in our solar system. That's a pretty wild thought. Part of what makes up our giant planets could be borrowed from another star's leftovers. And third, it raises the stakes for studying these travelers up close. We've only seen 3 so far: Oumuamua, Borisov, and Atlas. But soon that will change. The Vera C. Rubin Observatory, about to come online, is expected to spot dozens, maybe even hundreds of interstellar objects each year. That flood of data will finally let scientists test whether these bodies are common enough and heavy enough to truly act as planetary seeds. But astronomers don't want to stop at just spotting them. Imagine a spacecraft racing out to intercept one, instruments ready to scan every molecule, every isotope, every scar on its surface. A direct encounter could reveal its composition, its age, even its birthplace. Was it forged around a distant star and flung into space as debris? Or does it really carry the traits of a planet seed? Those are the kinds of questions future missions could finally answer. And quietly behind the scenes, those mission concepts are already being drawn up.
And of course, the big questions remain. How often do these interstellar travelers actually get caught by young disks instead of just drifting past? Even if they are captured, do they survive the chaos inside long enough to spark runaway growth? And perhaps the most important, are there truly enough of them out there to explain the sheer number of giant planets we see today? The good news is, these aren't questions that will stay mysteries forever. Over the next decade, with sharper telescopes and daring new missions, astronomers will finally get the data they need to test Falsner's bold idea. Maybe the answer will confirm her vision of interstellar seeds helping stars grow their worlds. Or maybe it will force us to rethink once again, adding yet another twist to the story of how planets are born. Either way, science wins, because every answer pushes us closer to the truth. So in the end, 3IATLAS might be more than just a comet streaking through our skies. It could be a planet's seed, a small, frozen clue to the origins of worlds like Jupiter, or maybe even Earth itself. The theory isn't proven yet, but the hunt for answers is already underway. And as new discoveries arrive, each one brings us closer to unlocking the cosmic recipe for building planets. The universe is still full of mysteries, and interstellar visitors like Atlas remind us that some of the biggest answers might just drift in unannounced. Stay tuned, because the next discovery could change everything we thought we knew about how planets are born.